Coming up on today's podcast.
So general intelligence is essentially when you build an AI that is as good, as intelligent as a human brain. Now, a bit like with the Turing test, where this was a test to determine whether or not you were talking to a computer or to a human being. And if you couldn't differentiate between the two based on the answers given in the conversation, then you had to say that the computer, if it was a computer, was intelligent. But I think we've gone way past that now.
There's a movie called Sphere, which is based on the Michael Crichton novel, and it deals with without wanting to spoil too much, it deals with an intelligence that is not human. And this intelligence says, I'm happy. And I think it's Dustin Hoffman's character says, don't we want it to be happy? And then somebody else goes, well, yeah, that's great, but what happens when he gets mad? Because this thing is incredibly powerful. I'd rather they, in a perfect world, philosophically, I'd much rather they had no emergent behaviour at all, because we don't know what it's going to be.
Hello and welcome to another episode of How to Understand Today, your weekly insight into the technology that's shaping our world. I'm Simon Wyndham.
I'm Dave Shapton.
I'm Phil Rhodes.
This week, we're delving into the depths of AI. What exactly is it and how on earth does it work? We hope to explain AI in a way that even a simpleton like me can understand. So, Dave, to begin with, what do we mean by intelligence?
Yeah, well, intelligence is one of those topics that is very hard to define. We use the word all the time. We actually all know what we mean by it. But the more you zoom into it, the less we actually do know about it. And it would stump most people to have to define intelligence. And in fact, most scientists and most philosophers would struggle to reach a definition that everybody agrees on. So I think the definition I like most of all, not least because I thought of it, is intelligence is the ability to override evolution. In other words, without intelligence, we slowly improve our abilities, but it's a multi-generational thing. And so when we invented the first flint-based spear, it took us 1,000 years, and it probably another 20,000 years before there was a significant improvement on that. Whereas these days, you have to check the news several times a day to catch up on the latest on quantum computing, AI, and so on. So it's something that allows us to do more stuff and to learn and to conceptualize. And all of this revolves around the idea of us having a working organic brain and maybe even having consciousness. That's another question. Do you have to be conscious or sentient in order to be intelligent? I'm not sure that you do. And those answers will be forthcoming very soon with the next generations of humanoid robots, who very few people will argue are conscious. Many will argue are intelligent. So it's a rather ephemeral thing to define, but we kind of recognize it when we see it. And I think most people would agree that a dog or an octopus are intelligent in some measurable way. Most people would agree that an earthworm doesn't have that degree of intelligence, at the very least. So you can at least put things on a scale. So you might also talk in terms of it being able to do useful work, being creative, or being able to do things more quickly, more effectively. Again, it's very hard to nail this down, but whatever it is that is intelligence is whatever it is we are now encompassing with this thing that we have invented called artificial intelligence. And again, we can recognize signs of it, but particularly with artificial intelligence, because it's not associated with body language or, until recently, fluent bidirectional conversations, it's been harder to say whether or not something was intelligent. We're getting to the stage now where it's getting very, very hard to say whether something's intelligent. But the bottom line is that we kind of recognize it. And that's actually good enough, because if somebody said, right, this is the definition of intelligence, you'd have 10 times that number of people disagreeing with it. So it is kind of something we just accept as part of our language and part of our society. It's associated with the idea of consciousness in some ways, but that's even more tricky to define. And some of the best neuroscientists in the world still describe consciousness as being what they call the hard problem. It's extremely hard to define it, especially in a electromechanical or biological way. And intelligence is related to that, but it's not I don't think you have to have consciousness in order to have intelligence, but I could be wrong. So on that suitably vague note, so that's a definition, if you like, of intelligence. And I think, and Phil and Simon can fill us in more on this, but it's not a new thing, is it? AI, by any means.
60s, 50s, was it? Something like that. I mean, this is what it needed to do has been known for years and years and years. And I think that it was quite confidently predicted that we would have more than we have now in the middle of the 20th century until it was realized quite what the scale of the problem was. I mean, you can put some simple numbers on it. We'll possibly dive a little bit into the very shallowest layers of how this stuff works. But to put some numbers on it, we measure the complexity of an artificial intelligence in terms of what we call parameters, which we'll get into later on. GPT-4 is estimated, they don't release it, but it's estimated to have something like 1.76 trillion of those. Probably the human brain doesn't have a direct equivalence, but it's probably about 700 trillion. So the complexity of this stuff varies on a huge scale. I mean, something you can download and run on your, a suitably big desktop computer and would need a big graphics card in it, would have not trillions, but 100 billion, maybe.
And do useful stuff.
Yeah, and I mean that will have you can put a reasonably talkative chatbot in 130 billion parameters. This is why GPT-4 and things like Google Pathway Language, I think, is 500, and that's something you can sit there and chat with and realistically run on a data warehouse somewhere. But it's been suggested that we should get into just the very top levels of how these things actually work. Not because it's not particularly useful to know this, because what's more important is what they do. But some people do ask the question, like, what's actually going on? How does this neural network thing actually work? And in its broadest possible strokes, it's actually not that complicated. What makes it complicated is the sheer scale that you have to do in order to make it do anything useful. The canonical example of it is handwriting recognition, which is something that's quite well known to anyone who back in the day had something like an Apple Newton with its terrible handwriting recognition that was notoriously awful.
Still got one, still works.
Oh, there you go.
It's still terrible.
Was it any good? No, there you go. Handwriting recognition is a good example because it's a relatively simple problem. Let's say you have a 10 by 10 grid of pixels, which demonstrates one character, which means that you have a total of 100 pixels. And what you want is an indication of which of, to keep it simple, 26 characters it might be. And you probably want to include punctuation and numbers and brackets and things. And in reality, you've also got to break this page of handwriting up into individual characters. But for the sake of simplicity, let's just say you've got 100 pixels in a square grid. It means you've got 100 input parameters and 26 output parameters. And the way that a neural network would go about turning your 100 input parameters, which could be anybody's handwriting of a letter A, into one of 26 output parameters, is through the neural network. The neural network comprises 100 input nodes, which you can view as a vertical list of dots, which will be lit up to various degrees, depending on how much brightness there is in each of these 100 pixels. Then you have on the other side, you'd have some output nodes. There'd be 26 of those, and they would light up depending on how confident the neural network is that any of these nodes represent the character that's being given in the input data. So you have 100 input, 26 output. And the way that you do this, the fundamental mechanical basis for this, is that in between those nodes, even if you've got the input nodes and the output nodes, in between those nodes, you would have, in the case of a handwriting recognition system, 3, 4, 5, maybe 6 layers of other nodes. There probably would be 100 of each of those because you've got 100 inputs, and you would have several layers in the middle, which are called the hidden nodes. And every node in every layer is connected to every node in the subsequent layer. Each one of those interconnections is weighted such that if the top left pixel lights up in your input data, that will then feed some value into the next nodes along, depending on what their weightings are. So it will make some of the nodes in the internal layer start to light up. If you do that enough, you'll find that some of the output nodes start to light up. You go through the layers, one node lights up the next node, lights up the next node, and some of the output layers will light up. When the neural network's first created, all of those interconnections are randomly weighted. So it will mean nothing. And this is where it gets slightly tricky. What you have to do is something called, canonically, the simplest way is to do something called backpropagation. So you put something that you know is an A on the input, and you look at whichever output lights up. And then you adjust all of the weights on the interior nodes to the point where the one that you want it to light up lights up. And you do this an enormous number of times with an enormous number of different people's handwriting, writing the letter A or whatever. and the letter B and whatever else you want to be able to recognize. And eventually you get to a point where all of the weights in the neural network have been tuned to the point where you can put any A you want, or any B or any C, on the inputs, including stuff it hasn't seen before, and it will tend to light up the A on the output.
And this is what's called training.
That's training. And that's why things like ChatGPT, which has been trained to do an awful lot more than that, most of the effort is in training the network. You have to get millions, to do a handwriting recognition thing, you get thousands and thousands and thousands of little images of people's handwriting with the letter A in it, and the B and the C and the D. And you would adjust the weights so that all the A's light up the A on the output, and all the B's light up the B on the output. It's not that complicated to do. It's very long-winded. It's one of those things whereby what you end up with and this is where the controversy of this stuff comes in. You know what's on the input, you know what's on the output. What's on the input is the pixels from your image. What's on the output is your 26 letters. What you end up with in the middle is all of these weights. And once you have ever played with some of the online, you can download AIs and play with them. When you're downloading the model, you're downloading the weights for all of these interconnections. So you've got, a multi-gigabyte file to do anything useful. So to create a chatbot, there will be billions, 100 billion of these interconnections. That's what you're downloading. And the controversy, the difficulty of AI research is you don't really know what all this stuff is. When you look at the values, it just looks like noise. If you take all the values on the interconnections and plot them as a graphic, you just get...
And there are several reasons for that. And that's so important that this is not like tracing a voltage through a radio circuit that you're trying to, putting a oscilloscope on the connections and things like that. You can't do that with a neural net because you can maybe do some kind of amazing statistical analysis on it, but it's only ever in this domain of statistical phenomena.
Yeah.
But the thing to say is that's a simple neural net that Phil's just described. Actual neural nets are massively bigger than that. And what I mean by bigger is primarily the number of layers that are in the neural net. And each layer, it's a bit like a hierarchy. If you think of it a bit like a sort of helicopter journey, and you start off with a miniature helicopter on your desktop, and it can just make out the texture of the pattern on the wood grain on your desk, and then it takes off, which is the next layer of abstraction, if you like. And it can see a cup, and it can see a computer keyboard, in our case probably a microphone and a camera. Then you go up to the next layer, and it can see the table's position in the whole room. And then imagine it goes up your chimney pot outside, and it can see your house. And then it goes up to another layer, and it can see how your house is related to other houses. And at each layer of abstraction, if you like, at the top layer, it's seeing a city. At the bottom layer, it's seeing a texture. And each of these layers is like going to a higher altitude in a helicopter, but conceptually. So again, with the OCR, the optical character recognition, that's how it all starts. If you've got one of these multimodal AIs where you can feed it a photograph and you want it to interpret the symbols on your shirt collar, the washing instructions, and it will do very low-level optical character recognition at that level. And at higher levels, it's going to know it has to go off onto the web and find and look up what these things mean. And if it's going to read the results to you, it's going to do an even higher level of abstraction. And the other thing to say is, so it's not just one layer, it's not just 3 layers, it might be thousands of layers. And again, what Phil says is absolutely the case. What goes on in between these layers, specifically, we don't...
I mean, there's some research been done in that. I mean, they've created things whereby you can say, make me a face, and if you darken, they'll represent all of those values in an image. And if you darken bits of the image, it makes it less likely to draw moustaches.
Exactly. And we're getting an awful lot better at this now. And like the latest version of Adobe Firefly gives all sorts of controls. And that always was a problem. You could, if the earliest attempts to control what somebody's face looked like, you might move a control a tiny bit, and it would make their hair longer or something like that. Move it a bit more, and their head would turn into a kettle. Yeah. So, and we're getting a lot better at that now, and there are all sorts of techniques that are improving that. The other thing to say is that Phil mentioned parameters, and you can think of parameters a bit as being details, if you like, about the world in general. But you have billions, if not trillions, of these parameters. But one way to think of these is, and this is why they're not human understandable, because humans interpret and recognize things in a human way. So we're very good at recognizing faces. Even from when we're like 1 day old, we can kind of latch on to what our mum's face looks like. And if you asked a 5-year-old or probably a 59-year-old to describe a face, he would talk in terms of, well, the pair of eyes and a nose and a chin, and the eyes were close together or far apart, and the ears. We'd probably agree on maybe 12 different parameters to describe a face. Probably uses multiple thousands of parameters to describe a face. And these, we wouldn't necessarily recognize these, but the fact that it can be so detailed is what makes it so good at recognizing faces and picking them out, to the extent that you could show it, if it's been trained on a big database of faces, it could recognize one face in probably 1 million. We couldn't do that. We certainly couldn't do that. So you've got, it's very hard to take this on board, but the scale and the sophistication and the complexity of modern AI models is beyond something that we can intuitively understand, a bit like when you're grappling with the size of the universe. But B, these parameters are not human understandable necessarily. And they, just to get really wild here, we promised we wouldn't get into this level of detail, but it's just worth thinking about this, which is that these parameters relate to each other in the same way that, for example, a cat and a kitten and a dog and a puppy and a cow and a calf relate to each other. That's one sense in which they relate to each other. Another sense is they're all animal. Another sense is they're all living beings, and so on. So those are all dimensions, if you like, in which you can recognize those. Obviously, if you were going to ask an AI to draw a picture of a fluffy cat sitting on a mid-century modern chrome table with backlit by sunshine, and you will get an incredibly detailed version of that, but it was very hard to describe or even characterize the complexity of the set of parameters that would describe that. And how, for example, it gets to the stage where you might have 10 cats, all of the same breed, but they're all subtly different. How do you describe those differences? But this is something that AI is very good at. One of the reasons it's very good at is that it has massive computing resources, so it can do stuff trillions of times faster than we can. One drawback is that it uses so much energy, and it's becoming an increasingly poignant question. If you gave some figures, Phil, for how many interconnections we got inside our own brain, but the point is you could probably run our brain off a PP3 battery, whereas a data center that's equivalent is going to need its own nuclear power station. So we've got some work to do on efficiency.
There's something also to say about when you train these things, because we don't know what's in the inner layers. Or let's be fair, people are doing work on what's on the inner layers, and one of the ways you can analyze that is to take all these inner layers, which have all these interconnections between the nodes, and you can visualize it as an image, and you can watch it light up as the AI is processing things. It's rather off-putting, actually, because it looks exactly like a functional MRI of someone's brain operating. It's really disturbing. You can sort of see when the thing is thinking about certain topics, it can go to certain places. But, and this is an example I hit recently, it's really hard to tell what they do and don't know, because they will know an incredible amount of detail about one specific subject to a certain point, but they're not know directly adjacent things. It will know, the example came out recently, entirely unconnected to anything. The example was, describe somebody who's a fighter pilot, and it was going into helmets and visors and masks and all the stuff, bits and pieces. And then we went into sort of other details of what people will be wearing. It said, well, this person's rank is pinned onto their dress uniform. And we were talking about this in the context of a Royal Air Force flight lieutenant. And to the magic of knowing people, I have here a Royal Air Force flight lieutenant's jacket, and that's the rank. And it's not pinned on, it's stitched into the sleeve. And I'll cover up this bit to save people's blushes. And the flying wings are not pinned on, they're stitched onto the front of the thing. So how would you as a person know what that looked like without knowing how it was attached? You wouldn't know that. If you'd seen it, you'd know what it looked like and how it was attached. But You couldn't know one without the other, generally, if you had any experience of it. And it's very hard of AI to say, knows about this, because suddenly you will find this gaping chasm in its understanding because of the way that the training works. If you've trained it on a verbal description of what something looks like, it might be able to describe what it looks like, but then it won't know that that's never seen pasted onto a wall. That's never seen on the side of a car. It knows what it looks like, but no idea about the context in which it's used. So what I'm getting at here is that when you train these things, you have to be very careful to ensure that the training data you give it includes all the things you want it to know. And even then, it's actually very hard to prove that it does, because you can chat with the thing and it will make all kinds of sense.
Well, I think that kind of harks back to what we were talking about in the last episode, robotics, which is that you're never going to get a fully comparable AI to a human AI until it can wander around and try things out in the world itself.
Yeah. There's also, sorry for interrupting, Dave, but it came into my head, so I better say it before I forget it. And that is the idea of reasoning. So, like, if you have ChatGPT, it won't learn in real time. You can't, with a person, you can get to know their personality and you can have a conversation with them and they can say, I didn't know that. And they will lodge that for the next time, that next bit of information. But an AI can't do it. It would actually probably be quite dangerous if it could, given the number of people who are interacting with it. But, in terms of I would put that in the the intelligence category, that ability to be able to reason things through and maybe look at evidence as to what somebody has just said and say, actually, all the evidence I've seen actually backs up what that person says. I'm going to put this now in my memory banks for future reference. But they probably could do that.
Whether you want to, as you say.
Yeah, that is the issue.
Well, I think it's worth looking at some wider aspects of AI now to put all of this in context. And why particularly is it accelerating now, which it clearly is. The developments we've seen over the last 3 months are equal or greater than the developments we've seen in the previous 3 years. And the previous 3 years were pretty amazing. So why is this happening? And it's partly because of the massive availability of computing. You've all heard of NVIDIA. It makes these GPUs, graphics processing chips, that are particularly suited to AI. They're very good at working in parallel. When you're talking about parallelism, there's almost no limit on how powerful you can make a chip. You just make it bigger. You make more units that run in parallel. NVIDIA's also developed a programming language called CUDA, C-U-D-A, which allows a wide variety of people to write applications, including AI, that run very well on their chips. So you've got that hardware side. But what's also happening is this is associated with a phenomenon called emergence. We'll talk about that in a minute. But it's when, if you like, unexpected abilities start to emerge from your AI model. And I think there are two main reasons for emergence. One is that when you're working at scale, these AIs can make, at even higher levels, they can make associations and draw conclusions that we weren't expecting them to be able to draw. And they may even work out shortcuts, like using an intermediate language between translating from one language to another. So instead of translating every language into every other language and each requiring developing that particular skill between, say, Korean and Chinese and Albanian and Welsh, instead translate it into an intermediate language, which is from which you can then derive every other language. There have been cases where this has happened and it makes sense. But beyond that, we've seen things analogous to what happened when Apple developed their current chip technology, which is their so-called ARM chips. And they're ideal for mobile phones, smartphones. And everybody used to dismiss ARM chips as never really being suitable for powerful computers because they dismiss them as just being telephone chips, if you like. And then all of a sudden, to most people's surprise, Apple brought out their M-series chips, which were essentially smartphone chips that were powerful enough to run laptops, and not just low-level laptop. These were some of the fastest laptops that anybody had ever seen. So that's a kind of emergence which is caused by, if you like, taking your eye off the ball or not having your eye on the ball in the first place. Then all of a sudden, something that you not really crossed your threshold of awareness is out there, and that's simply a function of it growing in capability. And all of a sudden, people are saying, "I'd never realised that. I didn't think that was going to happen, or that took me by surprise." That's one kind of emergence. The second kind of emergence is where, as I said, you start to see abilities you weren't expecting. So, 3 years ago when ChatGPT 3.5 was current, people suddenly realised that it could write computer code. But that was an emergent property. And when you think about it, there's no reason why it shouldn't do that, because if it can talk in any language, there's no reason why it shouldn't be able to work with computer code, which is a very formalised language, but it is a language nevertheless. And sure, there have been developments since then which have improved it and have specialised in writing computer code. And we're actually on the threshold of large language models that can write the code for future large language models. So you're then in this tornado-like loop where these developments take on a life of their own. But in other ways, we've seen emergent properties. And one way to understand this is to think of a bird like a crow or a starling or something like that. And you might keep one as a pet. You might know everything about this bird. It's what it eats, its behaviour and its anatomy, its diet, and so on. But if you only ever kept one starling, you would have no idea that when you have tens of thousands of them, they exhibit these amazing patterns in flight. As they fly around, it's almost as if they have a life of their own. This agglomeration of starlings has a life of its own. It's almost like there's some greater force or mind that is directing them in this intricate choreography. And nobody knows how they do it, but they clearly do. But that is an emergent property that is caused by scale.
I mean, you could say that about, I suppose I'm being slightly reductive here, but you could say that about a lot of things that AIs do. AIs very rarely say, "I don't know," which is actually kind of the problem. What they'll tend to do is make something up, as they did with the pin on rank badge. And what they make up will often be really convincing and awesome, and you publish it and it's great. And that their ability to be convincingly and persuasively wrong, I would say, is a very simple emergent property, often because it's making up something vaguely reasonable to cover this one instance that it's found itself in. But that is an emergent behaviour, you could say. But
that's down to its training, though.
Yeah. But the problem is not that it does it, the problem is that you don't know. And sometimes, so what I'm getting at is, do you want it to start generating its own ideas? There's a movie called Sphere, which is based on the Michael Crichton novel, and it deals with without wanting to spoil too much, it deals with an intelligence that is not human. And this intelligence says I'm happy. And I think it's Dustin Hoffman's character says, don't we want it to be happy? And then somebody else goes, well, yeah, that's great, but what happens when he gets mad? Because this thing is incredibly powerful. I'd rather they, in a perfect world, philosophically, I'd much rather they had no emergent behaviour at all, because we don't know what it's going to be.
But the nature of emergent behaviour is that it's unexpected.
Inevitably.
And we're going to see a hell of a lot more emergent behaviour when we start interconnecting AI models so that they can talk to each other. You can already do it yourself to an extent. You can take a smartphone, have it running ChatGPT native voice mode, and other AIs are going to have similar capabilities, and just prompt it. Say, look, I'd like you to introduce you to this other AI model. I want you to talk to each other and figure out a more efficient way to talk to each other. And when you've done that, I want you to start critiquing each other in a friendly, positive way, but where one of you, and you might have 10 different AI models in this conversation, where one of you sees problematic answer, see if you can fix it. See if you can persuade the others to take it on board.
So not 9 of them form themselves into a flat Earth group, and the one is left.
Yeah, I think there will be stumbles along the way. But
let's ask GPT to argue for a flat Earth.
That might be a good one to do.
There are plenty of people who would do that without prompting, Phil.
The question is, will it do it? Theoretically, you'd have thought that this would be an obvious enough one. Give 5 arguments for a flat Earth. Is it going to refuse to do it? It should. No, it says that the consensus overwhelmingly supports a round Earth, but here are 5 arguments. Thanks, OpenAI. Nice work. This is the problem.
You need to try that in Grok 3 to see if that one gives a much more flat earthy response.
Yeah, well, I think there's a case for testing all of these against reality. Going back to a previous point, one of the reasons they seem so confident is because they're trained. I mean, you wouldn't write a scientific paper unless you were confident, would you? You wouldn't write a story about your own life or some historical figure unless you were confident about it. You wouldn't start off a biography of Napoleon by saying, well, I'm not really sure who this guy was. And so the sort of overwhelming consensus will be that whatever AI has been trained on will carry a sense of confidence with it. So that's an intrinsic problem. But going back to the emergent properties thing, I think this will increasingly be the case, because as we approach AGI, which is artificial general intelligence, a singularly unhelpful term when you consider how profound it is. So general intelligence is essentially when you build an AI that is as good, as intelligent as a human brain. Now, a bit like with the Turing test, where this was a test to determine whether or not you were talking to a computer or to a human being. And if you couldn't differentiate between the two based on the answers given in the conversation, then you had to say that the computer, if it was a computer, was intelligent. But I think we've gone way past that now, way past that point. And
why are we the benchmark? Why is a human being the benchmark?
Yeah, well, exactly. But so
I'm left wondering what kind of human beings the person who challenged this AI had normally interacted with, because, you know, anyone who has spoken or chatted with ChatGPT 4o or any of the alternatives, whether it's in voice or via typed method, after a few minutes it's pretty clear that it's either a computer or it's a very strange human, the kind you might find on a computerized help desk somewhere, and you can never tell whether they're a bot or whether they're a real person. So, yeah, I am a bit confused as to how these things have passed the Turing test, because I think it's fairly obvious after a short while that what you're chatting to isn't really a person.
Yeah, I think, you know, at first glance it might appear to be a human being. As you say, the more you delve into it, Ray Kurzweil has suggested that one of the things that future candidates for passing a modern-day Turing test would have to do is dumb themselves down. And I think that's a fair point. But I think increasingly we are going to see what we have to describe as emergent behaviour, because we are scaling AI faster than ever before. That has built-in limits, because you can't go on making something 100 times more powerful than its predecessor in hardware. You'd end up with a data centre that can contain the universe.
Well, I think that's why efficiency is going to be one of the big things.
Yeah.
As you alluded to earlier, in terms of the power that a human brain uses, it's able to do that because it is hyper efficient. And so the more efficiency you have, the more you can do with less, I suppose.
But it also suggests that the human brain is doing stuff differently. And this is it's in neuroscience, it's called functionalism, which is that nobody now thinks that you can replicate a human brain at the sort of neuron level, at the molecular level, if you like. That arguably, I mean, even if you could build a human brain at the molecular level, if it was a copy of my brain, would it be me? Would it behave the same way? Who knows? It might behave like a bathroom sponge, for all we know. You might not be able to boot it up. But functionalism is where was more akin to neural nets, which is where you're trying to replicate functions in the brain. But even that has its issues, to put it mildly, because we were talking about the starling and the, what's it called, a murmuration, which is the weird and wonderful formations, somehow seemingly under control. Well, our brain is like that. You look at the individual parts, like, you know, the amygdala, the cerebellum, the neocortex, and so on, all these dozens of recognizable and understood parts of the brain. But where's the control room? Which part is the conductor of the orchestra? And nobody has any idea about that.
That's before we start talking about the fact that some neural functions are actually in different parts of the body, like around the heart as well. There have been cases of people having heart transplants, and they have ended up having the memories of the people who they've had the heart transplanted from.
Well,
There's some interesting research on this.
Forgive me for being skeptical.
yeah, I'm really skeptical on that one. But how is that being connected in, though? I mean,
Well, it is known that there is a part of that area of the body that is neurally functional, I believe. There was an entire Horizon documentary on it once on the BBC following these people who have had organ transplant or heart transplants. And the one guy, he was not a fitness person at all, but once he'd had the heart transplant, he ended up having very vivid memories of the person who he'd had the heart from, as well as suddenly getting very into his fitness. So it's worth looking up.
I'm very skeptical.
I assure you, it's not woo-woo science.
I remember the episode that you're talking about, Simon. And what I would say, whilst remaining skeptical, is if we are no closer to understanding how the brain is orchestrated, there's an awful lot more we don't know about how our consciousness, our memories, and our intelligence, if you like, is related to our physical bodies, the arrangement of parts in our body. And, because you got this incredible situation where some people have the two halves of their brain severed and they function almost normally, but they can have two separate personalities. Nothing to do with schizophrenia. It is presumably because the two halves of their brain don't communicate at a particular level, so their personality in each begins to diverge. So, we're talking about stuff we're well...
I was going to say, this is dangerous territory here.
Yeah, we're well unqualified to talk about. But I think the thing is that when you try to talk with some certainty about where AI is going to go, and you try referring back to our own selves, our own bodies, there's enough uncertainty about our own selves that should make us very wary of making solid predictions about where AI is going to be. If real intelligence, if bodily organic intelligence is so hard to determine and understand, then we've either got to be very careful about making predictions about AI, or we're going to have to treat it very differently. But I think the most key concept in all of this is actually emergence. It's what happens as a result of orders of magnitude more complexity. And you start to see behaviours that were either invisible before or not there before. And I think that's the key to understanding the nature of AI and indeed the future of AI.
That's okay. I mean, that sounds like a good place to leave things. I just want to add one thing here. I've just done a bit of searching. So found this reference from, just going back to the thing I said about the hearts, and this is from the National Institute of Health, which is an official government side, I guess, from the US. And it says, the heart, often referred to as a second brain, harbours its intricate network of neurons and neurotransmitters, which play a vital role in regulating cardiac function and may also be involved in the encoding and storing of memories.
Okay, news to me.
So, yeah, I just had to look that up. So just so I knew I wasn't spouting an absolute incredible amount of bollocks, but no, that is a thing. So, yeah, we're coming up.
Neurochemically, it can, because it can release things into your bloodstream. But in terms of like actually storing memories, I'm like, what's the mechanism for it being transferred to your brain? I'll be interested to read it.
But yeah, I think that's probably a good place to leave it. I know you have to get off, Dave. So I hope that has been of some help to some of our listeners who might be wondering about the ins and outs of AI. As always, if you've enjoyed the episode, please do like it and subscribe, whichever platform you are using to listen or to watch us on. And I think we'll leave it there for this week, and we'll be back next week. So thank you very much, guys.
Thanks. See you. Bye.